Hello and welcome to lesson 12 of our study of Mathematical Biology 1. So, in lesson 12, we learn how to derive basic reproductive number, that is R naught, using the next generation matrix. So, if you could recall from lesson 9, we used the next generation matrix to derive the basic reproductive number for the SEIR model. But in this lesson, we are learning how to use it generally to derive R naught for any model that you have. Okay. So what is basic reproductive number R naught? So basic reproductive number R naught is defined as the number of secondary infections caused by a single infected person in a completely susceptible population. So if our R naught is less than 1, what it means is that the disease will be dying out. Okay, so the R naught definition, what it means is that, for instance, we have a population of 100 people, right? None of them has the infection. Then one person gets an infection and enters into that population of 100 people, right? So the number of people that person gives the disease to, let's say we can say per day, is what we term as the basic reproductive number. So if it is less than 1, then what it means is that the person who has the disease cannot give it to anyone. Do you get it? So that means the disease will die out. And if it is 1 or more, then it means if one person has a disease, that person can give it to at least one person. And that means the disease will what? Spread. So that's what we mean by the basic reproductive number R naught. So if R naught is less than 1, then the disease will die out. If it is greater than or equal to 1, then the disease will spread. So if it is equal to 1, then we are going to have an endemic. So endemic means that the disease is going to spread though, but it is going to spread at a very, very slow rate. Okay. And it will occur in the community for a very long time. And if our R naught is greater than 1, then we are going to have an epidemic. So epidemic means that the disease is going to spread at a very, very fast rate. Okay. And so occur in the community for a very short time. So now let's go to the steps in deriving R naught using the next generation metrics. So what we do is that we go into the model, whatever model that we have, and we regroup the equations in the model into disease classes and non-disease classes. That's the first thing we do. After doing that, we then take the disease class and we rearrange the equations in it to conform to something like this. Alright? Where our Greek f of xy is a term containing the secondary infection rate beta, and Greek v of xy contains other terms. Okay. Alright. Then after getting our Greek f and Greek v, we have to obtain f from this and we have to obtain v from this. So we obtain f, a matrix, by differentiating the terms in Greek f partially with respect to the original dependent variables. So what this means is that if our dependent variables are 2 or more, f will be a matrix. But if our dependent variable is just 1, then we will not have a matrix. Okay. We'll solve an example to illustrate that. Then we obtain v, a matrix, by differentiating the terms in Greek v partially with respect to the original dependent variables. So after that, we find the product of f and the inverse of v. So after finding for the product, if the result is a matrix, then we find the eigenvalues of fv inverse and we select the dominant one, which yields our basic reproductive number R0. So let's take an example. So we consider the SIR model with vital dynamics and force of infection. So the model equations are what you can see on your screen. So we have three equations, right? This here just shows that the total population is divided into three equal parts. No, sorry, into three parts, not three equal parts. Those who are susceptible, infected, and have recovered. So we have three equations here. And out of this equation, when you take the first one, the people here are susceptible, right? This means susceptible means they don't have the disease, but they can have the disease upon exposure to an infected person. So that means people here are what? Healthy. When it comes to the third equation, it contains people who have recovered, right? And in the SIR model, we assume that people who recover have permanent immunity. So that means the people in this class are also healthy or healthy. But when it comes to the second equation, the people here are infected. So this is the only disease class we have for our SIR model with vital dynamics and force of infection. So that means this is our disease class, and putting it to correspond to this form, right? Remember, this is a general form. We will have our Greek F to be this, and our Greek V to be that. And here, one thing you should know is that we have just one dependent variable, that is I. Alright, so we will have Greek f of I will be this, and Greek v of I to be also this. Okay, so we have just one dependent variable, that is I. So mostly when we get here, what we do is that you can see we have an n here. So we always scale to get rid of our n. Okay, and so by scaling, we will have Greek f of I will be equal to beta xi. You can see our n is no more there because we've scaled it. So now we have this to be our Greek f of I and our Greek v of I. So the next thing is that we have to find f and v. So we find f from Greek f and we find v from Greek v. So since we have just one dependent variable, f will be equal to the Greek f di. So this is the Greek f. When we differentiate with respect to I, we'll get beta s. Then vein to be the Greek vein di. So there's that one. So when differentiate with respect to I, we'll get mu plus gamma. Alright. So after getting this, then you see when it comes to the f, we have s here, alright, which happens to be a variable, not a parameter. So we evaluate f and v at disease-free equilibrium point. That is s star I star equals 1, 0. So since we don't have any variable here, this will give us the same thing. But for f, we will have beta times 1 because s is 1, which will give us beta. And we will get v to be mu plus gamma. So now we are looking for f v inverse, right? So you could see since we had just one dependent variable I, we are not having a matrix in this case. So we have f and we have v. That means we can find for inverse of v. And the inverse of v will be the reciprocal of what v, which is 1 over mu plus gamma. Then the product of f and v inverse will give us beta times 1 over mu plus gamma, which will give us beta over mu plus gamma. And this corresponds to our R naught. So that means saying using the next generation matrix, the R naught for this model is R naught equals beta over mu plus gamma. Okay. If we had not if we had not evaluated f at the disease-free equilibrium point, our s would have still been here, so we would have had R naught equals, let's say, beta s over mu plus gamma. And I'm sure this is something you've seen before. Okay, so with this one, if we had not evaluated our f at the disease-free equilibrium point, we would have had this because the s would have still been there. So don't be surprised when you also see this in other textbooks. Okay, so example 2. So we talk about the SERR model, but the equations here are different from the ones we discussed in lesson 9. So the model equations are what you can see on your screen. So you can see we have 4 of them. So we have this, that, this, and that. Right, so we know here people here are healthy because they are susceptible. People here have recovered, they are healthy. Right, but when it comes to the 2 equations in the middle, we have people with the disease there. Okay, so this one are people who have been exposed to the disease, and as a result of that, it makes them potential infectives. So this is a disease class, and this is people who are infected and can transmit it. So we also have a disease class here. So that means for this model we have 2 disease classes. So that means you're going to have a matrix. Okay, all right. So the disease classes are these 2 equations. All right. So because we have n, we can scale to get rid of it, right? So by scaling to get rid of n, we have the e dt to be beta si minus what you can see here. We just get rid of the n. So it's the same thing we are writing, just that in this time, like this time around, we don't have any over n. And this is the I dt. After getting that, do you remember our Greek f contains term with what? Secondary infection rate beta. So when it comes to the first equation, this is the term containing beta. It was beta Si. So we have that. But in our second equation, we don't have anything containing beta. So that means the component there is 0. Right? So after that, everything left goes into our Greek what? Vein. So that means here after that, everything here goes into our Greek vein. In here, everything here goes into our Greek vein. So that's how we get our Greek F and our Greek vein. So from here, we are supposed to form our matrices F and vein. So the dependent variables are E and I. Okay, you can see we have E here and we have I here. That means since we have 2 dependent variables, we are going to have partial derivative because we will differentiate partially with respect to one and with respect to the other one too. So in our Greek f, we let small f of ei correspond to this and g of ei correspond to that. Okay, so that means that our f matrix or our Jacobian matrix for f will be del f del e del f del I, del j del e, del j del I. So doing that will give us, so when differentiate it with respect to e, mm, okay, so oh okay, so differentiating this with respect to e will give us 0, and with respect to I will give us beta s. So that is this our f. Okay, and since our j is 0, all of them will give us 0 0. Okay, so evaluating at the disease free equilibrium point, we will get s star, I star, e star to be 1 0 0. Right, so that wherever you find s, we put 0 there. That will give us this. Okay, so I'll just have to interchange these two. Initially when I was writing, I brought this one here instead. So beta times 1 will give us beta. So that means our f will be 0 0 0 beta. I hope we get it. So this happens to be our f matrix. So we are good to go. Now we have to find for our vein matrix from the Greek vein. So from our Greek vein, we let f of ei be equal to this, and g of ei be equal to this. So these are Greek vein. So we let this be f, a function of f, and this be j. Okay. Okay. Right. So we find del f del e. So when you differentiate this with respect to e, we'll get this. With respect to I, we get 0. Then when you differentiate, okay, this place is I. Oh, we can see that it is I. There we have I here. Okay. So when you differentiate j with respect to e, you get kappa. With respect to I, you will get minus gamma plus mu. Okay. All right. So after getting this, we can choose to evaluate it at the fixed point, but since we don't have any variable here, we get the same thing because we just have parameters. Okay, so just have to bring my negative here. So this becomes our vein. So now we have to find for vein inverse. Vein inverse. Alright. So to find for vein inverse, when you have a 2 by 2 matrix, say A, B, C, D, finding for the inverses, you have 1 over the determinant, which is AD minus BC. Then interchange the position of these two and you negate the others. Okay, right, so that means that we will have the determinant. So the determinant will be the product of these two times the product minus the product of these two, but since we have 0 here, that goes to 0. So because we have minus here, we attach it here. So this will become the determinant. Then we interchange the position. So recall we have minus here. I omitted that earlier when I was writing, or I'm bringing it. So we have something like this, and we negate these two, right? But negative 0 is the same as 0. So we have something like this. Then we multiply through. So multiplying through, you can see that here the negative will cancel the negative, and gamma plus mu will cancel gamma plus mu. So we will get this. Then here 0 times any number is 0. Then here our k So we get minus k times this. So the minus minus will give us positive. Alright. Then here, because of the negative here, we also have negative 1 over gamma plus mu. I hope you get it. So now we have V inverse. Now you have to find the product of these two. So let me bring my negative here. Okay. So multiplying these 2 by 2 matrices, we have 0 times this plus beta times this. So we don't have any negative here again. Yes. So plus beta times this, which will give us beta kappa over whatever we have here. Then we will have this times this times this time, which will give us 0. Okay. Then you have this time this plus this time this, which will give us minus beta over gamma plus mu. Then the other place also give us 0. So here we find the eigenvalue. Okay, but since our matrix is in this form, that means the eigenvalues will be the diagonals elements, right? So our eigenvalue will be beta kappa over mu plus kappa plus r1 or multiplying gamma plus mu, and our lambda 2 will be 0. So we find the dominant, we find the absolute value of these two, right? So there is no negative here, right? So when you find the absolute value of this, you get beta kappa plus blah blah blah, and absolute value of 0 is also 0. So between these two, we ask ourselves which of them is larger between this and this. So lambda 2 will always be 0, but since we have beta kappa being parameters and they are all greater than 0, that means whatever we have here will always give us something greater than 0. So lambda 1 will be the dominant of these two eigenvalues. Okay, so it means that beta kappa over mu plus kappa plus r1 all multiplying gamma plus mu is the dominant eigenvalue, and that yields r0. Hence r0 is given by this relation. So that is how we use the next generation matrix to derive the basic reproductive number r0 for any model. Okay, so thank you very much. I'm Bodo Kanrinov, a final year student of mathematics at the Kwame Nkrumah University of Science and Technology, Ghana, West Africa. Please like the video and subscribe to the channel for more content like this. So in our next video, we will talk about sensitivity analysis. Right? Thank you very much and see you in the next video.